Okay, thank you.
Right. Welcome to our seminar series. Welcome to the fourth and the last week of our program. All right, and I'm very pleased to introduce our first speaker this week, Professor David Sigmund from Stanford University.
Thank you. So let me preface this by saying this is a talk on a subject that's in development. I would certainly welcome suggestions. You'll see that there are many spots that are a bit rough, although I think we're also making interesting progress. And it's a very challenging problem. At least the problem we're trying to deal with is very challenging. So we're talking about genomic analysis where there are local signals, in this case, insertions and deletions in the DNA, which we hope to detect by sequencing methods, so-called resequencing. Some people call next generation sequencing, but that sounds rather pretentious to me, so I'm using the term resequencing. We're assuming we have a basic genome sequence, and now we're looking at several candidate genomes, one or more, to see if they're missing something or if they have something extra added at different places in the genome. And that's what we mean by insertions and deletions. There are a number of other problems that have the same, roughly the same flavor, and so I'll mention a few of those as we go along. But let's move to this deletion schematic. So here's our standard genome, and here's a target that we would like to study, and we study it by so-called paired end reads. That is, we take a segment of the genome, of this genome, that presumably has known length. Now there's some random deviation in that known length that causes a little problem, but has a known length of roughly maybe 200 to 400 base pairs. And we sequence a little segment from each end. A question of design is how long a sequence do we want to take? A few years ago, 36 was a standard number, 36 base pairs. Now 100 is a standard number. A longer sequence read creates more errors. So there is a little question as to whether longer is better. We can't afford to read the entire sequence, so we read, as I say, a segment from each end. Then we map that to this position. Now, this one maps faithfully up to here, but this region is, this region in the reference genome is missing in the target, and so this point maps way over to here, and that means that where we started with, we think, maybe 200 base pairs, it may look like something that's where these are 400 base pairs apart, and that's an indication that we've of seeing deletion. If the picture goes the other way around and there's an insertion in the target compared to the genome, then the distance here will appear to have shrunk. Now, let me make a remark that there's a much easier version of the problem where we only consider a single end read. If we only consider a single end read, then what we'll see is we don't get any reads that are in here. So if we have sort of an average number of reads as we move along here and all of a sudden we see none at all, then that's evidence for a deletion. So single end read problem is statistically much easier, but it's also much less powerful. So we're going to work with the paired end reads. Now, here's a toy model. It has some defects and something we can learn from. So we're going to talk about it initially. We can detect these structural variations. We assume that the DNA fragments are of equal length, typically about, as I say, about 200 400 base pairs. And when the fragments map faithfully to whatever length they are, that is delta plus or minus error, we observe a distance between these ends that is normal with mean delta and variance sigma square, assuming that the only thing that causes us a problem is measurement error. And generally speaking, if we try to take longer reads, that is longer delta, then we'll get larger sigma squares. So that's part of the question about design. What's the trade-off here? And when there is, say, a deletion, there's some percentage, which I'm going to denote consistently by R, of the Ys which are shifted, where the distribution is shifted by an amount W. And W is the width of the deleted region. Now, I've been inconsistent between this line and this line. The shift, here I've acted as if the shift takes place between tau minus delta, tau being the point where the deletion begins, and tau, and here I've written it tau to tau plus delta, where this would be the point where the deletion begins, but it's just a typo. For an insertion, the shift is apparently less than 0, which, as I say, is a reflection of this picture we had here. When there is this deletion, then what should be of length delta here appears to be of length delta plus W, W the width of the deletion. And now typically, even with a single individual, we'll have, this stands for a single DNA sequence, and each individual, of course, has a pair of DNA sequences. So typically there will only be the deletion in one of the two DNA sequences of an individual, and therefore there's a fraction, and that's the fraction R, which may be 1/2. If we're dealing with a single individual, it would typically be 1/2, which show the mixture distribution. That is, they show 50% of the Ys will be from the nominal distribution, and 50% will be shifted by an amount W. But we may want to do this for larger, with so to speak, pooled DNA now. It's all being done in silicon, so we're not talking about pooling the DNA in order to do the resequencing. We're talking about pooling the DNA in order to do the analysis. In cases where we think that we're not getting enough reads to do it with a single individual, we may, as I say, pool the DNA from several individuals. Or if we want to study the population relations of different individuals, again, we may pool the DNA. So N as a process stands for the number of reads, say, to the left of the point tau, and then we have this simple-minded mixture model as our first candidate model to try to study. Delta is in principle a known parameter because we've taken tens of thousands of these fragments and we can measure their average length. Sigma square is, for the same reason, in principle a known parameter. W is unknown. R we will end up treating as known, even though in many examples it's unknown. It turns out that we can put in a nominal value, a small nominal value, and it's pretty robust. But in principle, R is also unknown. And as I say, at the change point, which in this notation is tau minus delta, the distribution of our observation shifts from the nominal to a mixture of the nominal and the shifted normal distribution. Okay. And so we can, if we formulate this assuming that we're talking about a Poisson process, then in general it's going to be non-homogeneous. And again, another question is, do we really have to deal with a non-homogeneity, or can we just assume that there's sort of an average amount of coverage? This refers to the when we have this sequence and we fragmented it, we have all these intervals, and the question will be, do we have lots at a particular point T, do we have lots of these intervals covering T, or do we have only a few? And because this will not be homogeneous as we move along through the genome, we will nominally think in terms of a non-homogeneous Poisson process. And then of course, because we're talking about two ends, there's the left end, which is described by T, and the right end, which is described by Y. And so this is the length of the fragment, so the distribution of the length of the fragment. And then we have a null model, which is under the model that I wrote just on the preceding slide, where this is a normal with a known mean and variance. And then we have an alternative model, and typically we take the alternative model to be a mixture of the known model and the known model shifted. And as I say, both R and W are usually assumed to be unknown. And if we look at an interval, if we assume that we have either lambda 0 or lambda 1 throughout the interval, then we can write down a log likelihood function, just integrating the continuous parameter Poisson random field. Now, here are a number of related problems that I want to mention because I think they can be dealt with by the same method. And ironically, it turns out that just poking around in some of these other problems is helpful for our problem because we learn to deal with a few simple models that have some peculiar features to them. Here's one, very nice paper by Schwartzman and others in just 2 years ago, where they consider a problem of so-called chip sequence analysis, where, which I won't try to explain, but it involves a similar problem, but where the signal is in the form of the convolution of a Poisson, sort of the same Poisson process we're talking about, with a smooth kernel because of the way the data are collected. Instead of getting a real change point problem, or what you might call a real change point problem, they get a smooth signal. So instead of having something where the signal changes abruptly from getting sort of normal data to a mixture of normal data and other data, they will have sort of a smooth version of this signal. And so they consider a model with a convolution of a smooth function with the underlying Poisson process. And again, we can write and now I'm going to consider a formal log linear model, although there's not any particularly good scientific reason for doing it. And so I will try to continue to refer to it as the formal model rather than the real model. In fact, the real model is this so-called real model is the mixture model I've described. The exponential family model is something else, but it will be useful for calculations. So there's one related problem which we can deal with. Another one is that depending on the care with which the data are taken, the Poisson process is often, or what we hope would be the Poisson process, is often over-dispersed. And a standard way for approaching this is a negative binomial process. So I just remind you that we can do that with a gamma mixture of Poisson processes. And if we want to preserve identifiability, we'll have a constraint on the mixing parameter of the gamma distribution. And then we get a slightly different log likelihood. And if this parameter alpha is infinitely large, the alpha here in the gamma distribution, then we get back to the Poisson model. Okay, and so I think it's true. I haven't checked this line by line. We seem to be dealing with a Poisson process in our data. But I think anything can be done for the Poisson process can be easily done for the mixture, for the gamma mixture. So to get back to the paired end reads, which is our, and let me make one more remark about the scale of the problem. When I talked here before, one of the problems I talked about was so-called copy number variation, which in many respects is very much like insertions and deletions. An insertion representing a gain in copy number, a deletion, a loss of copy number. But in that case, the data from several years ago was data from SNP arrays, and in SNP arrays, a single observation represents something on the scale of 1,000 base pairs. Now we're talking about the possibility of detecting insertions and deletions on the scale of 5s or 10s of base pairs, or even a single base pair. So the scale is completely different, which is why we are going through the same exercise with, roughly the same exercise with sequence-based data. And because it's sequence-based data, it's much more sparse, and so we're using a Poisson model rather than a normal type of model. But in some respects, the problem is very similar. The differences are more or less largely technical. So here's the abstract model I formulated, written in the form of the formal exponential log linear model. So I have this nonlinear kernel. I'm integrating that with respect to my underlying Poisson process. It's got this parameter tau, which is really where all the action is, because tau stands for position in the genome, and other things like the width of a deletion or the frequency with which the deletion occurs, the two parameters that I introduced before, W and R. Here it says that. So tau denotes, just in an informal way, all of these parameters. And so we have to write this more explicitly if we want to do actual calculations, but we can learn something by writing it this way. And as I said, I've written down this model in a way that's log linear in beta. Beta equals 1 actually corresponds to the original model with the right interpretation here. That is the likelihood function that I'd written, which we've now forgotten, in this form. With the appropriate choice of this kernel, K, that's the K sub, in this case, K sub T of Y. This can be, the value beta equals 1 corresponds to the actual mixture model, but I've embedded it in this larger family, which is log linear in beta. And as I say, I refer to this as the formal alternative because it's a convenient technical device. It's not something I think is true unless I specialize to beta equals 1, and then it's subject to the usual kind of fictions, but not an extra set of fictions as well. So if I do write this a little more specifically in the form of the two-dimensional Poisson field, explicitly expressing the two dimensions, that is the interval from t to t plus delta, and then the length of the fragment dy, I can do more specific calculations. Now the reason I've sort of written this out is to emphasize that we might choose to look at what's basically the raw data, or we might choose to look at the log likelihood ratio. And we're going to look across the genome, that is, we're going to vary this as a function of t, and we're going to look for peaks of one kind or another. That is, we're going to look at the local maxima of this process as a function of t, because that maxima indicate that we're at the point of a location, the location of a insertion or deletion. Now, so I've written down some terminology, but the main point is we might choose to look at the data itself, the data themselves, or the log likelihood. If I fix W and R, which is my initial idea, if I fix W and R, then these two things are completely equivalent, because this being greater than or equal to some threshold is equivalent to this being greater than or equal to some other threshold, just rephrased, because everything here is something that I can compute if I fix W and R. If this max stands for a maximum over T and W and R, or W or R, then these two are not equivalent. And so I think sort of the first question I'm going to ask is, well, maybe the second question. The first question is, how do I control false positive errors? And I do that using the exponential family embedding. So if I'm given W and R, and I've only written down that case, then I use the exponential family, introduce an exponential change of measure with Kullback-Leibler number playing a critical role. If that's the threshold X, then I equate the Kullback-Leibler information to X at the exponential parameter beta, the fictitious parameter. And then I can write down a pretty decent approximation to the probability that when I maximize this, and here I've written over maximum over T and over W. W is definitely unknown. And so I might want to maximize over W, or I might want to choose a nominal value and just hope that it's adequate. If I do that, then as I say, I get an expression. It's basically a tractable expression. I have to do some computations in terms of derivatives with respect to the parameters of the log likelihood. And we could, if we wanted to, consider maximization over both W and R. So let's assume that I've done that and I'm happy with type 1 error approximation, and I'm more or less happy with it. It's not as good as it might be, but given the scale of the problem where this maximum over T easily can run into the millions, it's not something that's very easy to simulate. Although maybe it would be possible to cook up an importance sampling algorithm. I haven't really tried to do that because I think the approximation is good enough, but I'm not going to produce any evidence of that. I'm just going to ask you to accept it. But here's sort of the insight I've tried to get out of this model, which, as I said, is not a great model, as we'll see in a moment. I've taken an arbitrary value for now I have switched also to the case of a homogeneous Poisson process, which you might have noticed that I started out writing rho of T, but now all of a sudden it's just rho. I switched to a homogeneous process, again, for the sake of simplicity, but I'll try to argue that it won't make a whole lot of difference. Anyway, I've taken a nominal value of R, which is 0.1. Then I've taken different values of R, which may or may not be equal to 0.1. I've taken a nominal value of W for a couple of these statistics. Well, for this statistic, and W is equal to W1 for the so-called optimal statistic. And R is equal to R1. So that's a statistic it's not a statistic because it depends on assuming I know parameters that I don't. This stands for the likelihood function where I've taken W to be 2, and I should say here, consider W's in this range. This is on the scale of 10 base pairs. So 0.5 stands for 5 base pairs, and 5 stands for 50 base pairs. And so this is nominally 20 base pairs, and nominally R is equal to 0.1, as it is for these cases. Here's Z is equal to the parameter R is equal to 0.1 here, but I've maximized out the value of W over this range. Here, let me skip that one. It's not terribly, in the end, it might be very interesting, but it's too complicated to try to explain at the moment. Here's L, where again, I've taken R equals 0.1, I've maximized out W. Here's L2, where I've maximized over both R and W. And I suppose the point I'd like to try to make is, with these numbers, and what I've computed is so-called marginal power. That is the power you would get if you focused if you were sitting right on top of the thing you're trying to detect. Not moving around looking for it, but sitting right on top of it. That maximizing over both R and W seems to be trying to do too much adaptation. even when we get down here to where R and W are not the same as, not close to the nominal values, or here's a good example, where R is 0.5, so it's not close to the nominal 0.1, still optimizing with respect to R as well as W doesn't do as well as optimizing just with respect to W by itself. I think there's some place where it does better, but I don't see it. Nope, no place there does it do better. Working with a likelihood ratio seems to be slightly preferable to working directly with the Z statistic. Working with the nominal W as well as adaptation with respect to W, but not R, seems to do a little bit better, I think. Well, not there, but when we get down here to where adaptation with respect to W might help you, it seems to help you somewhat. And so my judgment is that this is the best of these statistics that I've considered, with the exception of this one, which I'm not, as I say, I'm not trying to explain, which involves a Bonferroni type of correction. However, in a few minutes, I'm going to concentrate on one of this kind. It's enough simpler to analyze and doesn't seem to be so bad that I'm not willing to consider it. Okay, so I said that in principle, rho should be, we should be talking about a non-homogeneous Poisson process. And what does that mean? Well, it means there are going to be values where rho is small, and if rho is small, then the threshold I put can be rather small, because the value of rho will generate the level of the noise. Of course, it will also generate the level of the signal. But the point is that if rho oscillates, my threshold in principle can oscillate also. And if I keep rho fixed, then there's no reason to change the threshold. I might as well keep the threshold fixed. So you might ask the question, suppose that I have a region rho, but I use, where rho is something different from what I assumed, then I'm going to lose some power if rho is small. So for the scenario I described on the preceding slide, if rho is 0.5, the 0.05 threshold, accounting for multiple comparisons for the statistic L, was 12.05. The marginal power for that, when R1 is the nominal value and W1 is one value within the range over which I've maximized, was about 0.8. Now, suppose rho has actually dropped down to 0.2 because I'm in one of these regions where there aren't many points, period. Now the correct 0.05 threshold would be about 11.54. The marginal power would be about 0.34. But if I don't account for the dip and use, in fact, the original threshold, the power would be about 0.32. So I've lost a considerable amount of power. I've lost power from 0.8 under the best of conditions down to 0.34. And if I use the wrong threshold, it would be 0.32. So most of the power that I've lost is just intrinsic to the change in the situation. I'm not getting as much signal. I'm not getting as much noise either, but compensating for the lack of noise by trying to fine-tune this is not very helpful. And there are many calculations. Now here, I've only lost, my rho is 40% of what it was here. It can really dip down to something very small, and that's subject to some more investigation. But I've looked over some reasonable range of values, and you just don't get much in the way of additional power by trying to optimize with respect to this rho, which, as I say, in principle, and so optimizing with respect to it is just doing the work that it takes to study the non-homogeneous process. which does require an extra dimension of integration. So it's a pain in the neck. Now, let me come back because the model that I did describe is not completely adequate. So this was the picture I showed you before. Here was a deletion in the reference, and I drew a picture which showed a point that mapped across the deletion in the target, and then the length of that gets expanded in the reference. But there's another possibility. This is difference. This is a different picture. Here the target has an insertion in it, but the same thing would be true with the deletion. Here, there's no reason that this thing has to go all the way across and therefore get mapped in a way that's consistent with this picture. One end can fall inside now in this case, the inserted region, and that end won't map because there's nothing up here that will map it. That means we have what we call hanging reads. Now, there are different possibilities. Half of it might map. That is, it might fall right on the junction, and you might be able to map half of it. But that's a fairly complicated problem, and since you don't have the whole length of the read, the mapping accuracy will not be as great and so forth. But there are other possibilities. But we're just going to consider one other possibility, which is so-called hanging read. And that's where one end, as I say, one end maps, but one end does not map. And if I do that, I can write down a different sort of model. Now, here's the original model, where I've written the mixture part rather more carefully. So it's not quite, it's a little more complicated than the mixture model I wrote before, but it has the same flavor. And there's a null model, and then there's the kernel, which gives me my mixture. And for some reason, I decided sigma square was too difficult to write in my computer program, so I replaced it by its reciprocal. So c squared is 1 over sigma squared. But here's the other piece. Here's the piece where the left, and now I have to say something more. I said we just look at these, we sequence the two ends of the strand. In fact, there's every strand of DNA is a double strand. And you break it apart, you sequence the left-hand end from the so-called positive strand. That's the strand you read in the direction that everybody but the Israelis and the Arabs read in. And then you sequence the other end from the negative strand, which the genome reads, and it reads it from right to left. So this is the component of this hanging read statistic, which comes from the positive strand. There's another segment that comes from the negative strand, which I've written as if it's obvious what it is. And I'm talking here about deletions, and now I probably have to be a little more precise. This accounts for, this is a log likelihood term that accounts for the possibility that this thing is just long enough that it falls on this inside this critical interval in this case. And then it will be hanging with regard to the reference genome. Now let me, at the risk of messing up everything, draw two slightly different pictures. Here's the insertion. Now, so here's the reference genome. Here's the insertion. There's an insertion from tau to tau plus W. So this material is not in the reference genome. That means this point will map faithfully to tau, but this point here, or this point plus epsilon, will map to tau plus epsilon. So we have this thing. So a hanging read here, anything that falls into here, will, when I map it, will look like it's hanging at the point tau. Anything from here, which gets read in the negative, in the other direction, that falls into here, will also look, because these points all get mapped down to here, will also look as if it gets hanging at the point tau. That's a fairly simple picture. Was I going to try to say something else about it? Oh, and you see here, the longer, up to a point, the longer this interval is, the better off the situation is, because anything that falls in here will be a hanging read. So generally speaking, when you have insertions, you get more information the longer the insertion. Now let's draw the same picture for a deletion. Here's the standard genome, and it has something in it that's not in the experimental genome. So now this point maps faithfully to this point, but this point maps out to that point. Now, first of all, what happens? We draw this same picture, and now this has to actually split. It has to split at that point. There's not an interval for it to fall into. It has to split exactly at that point. So it doesn't depend on the length of this interval at all. And now you get a hanging read. Now, if you read in the other direction, and same situation, this point maps way out to here. So you get a hanging read out here. So the positive strand and the negative strand gives you hanging reads that appear to be at different positions. And that means that you might try to line them up, which is what I've been trying to do over the last few days, because first I thought it wouldn't make much difference, but now I think it does. That is, you might try to, since in principle they both come from the same position in the target genome, you might try to, instead of taking a likelihood function, which will have a parameter tau and another parameter tau plus w, that you might try to push them together by maximizing with respect to w. In other words, when you read this and you're looking for a little peak, what you're going to see is a little peak there and a little peak there, one from the positive side and one from the negative side. And now we might say, well, can't we just add those two together somehow? We could add them together. We can add them together in this case because they're going to fall in the same position. Can't we add them together in this case by looking for this and then aligning them? Okay. Now, as I say, we see if this will come back. Ah, good. So I've written this model, not with any great detail, because I think you learn a lot more from what I've tried to draw than you could possibly learn by looking at these integrals, although they're supposed to reflect the picture accurately. And now here are features of several public data sets. Aha. Oh, I should say one other thing. You might think, well, if I see this picture down there, oops, forget that. If I see one of these hanging reads, everything's obvious. And the answer is no, it's not obvious. There is a rate of failure. And as long as I'm talking about the other part of the model, that is the mixture distribution, the rate of failure to map something correctly is so small that it hardly makes any difference. But I'm now introducing another parameter, p, which I didn't properly point out when I was writing this. Under the null hypothesis, there is a possibility that you get what appears to be a hanging read. That is, you just have a mapping failure. If you have a mapping failure, you don't get anything at all. And that's what happens. That's what happens here that causes so-called hanging read. You don't get anything. This doesn't map, period. Now, it doesn't map means what might mean it mapped over here 10 chromosomes away. Or it might mean that you just made a mistake. The sequencing wasn't correct, the computations or something weren't correct, and it just didn't map. Now that probability is pretty small, but you have to account for it in the new ingredient here. I should also say that if you look at these parameters, this is the probability that you reach I think this is the probability you reach at least as far as the point where you fail to map, and this is the probability that you don't reach a whole lot farther, because then you'll be back on the other side and you will map, or you should map. P is the new parameter that says the probability of incorrect mapping. And we can, again, this is the model for deletions. There's the corresponding model for insertions, which I've tried to illustrate on the blackboard. And here are some figures that we're still trying to digest with regard to data sets that are publicly available. And as I said earlier, an early data set, a typical read length was 36 base pairs. The goal was to have these segments be 200 base pairs long, and I don't know if it's important that I show you exactly what that means. Maybe I should. Let me just do it in the air. You have these two reads on both ends. The length of the segment, the insert length that's called delta, is from the beginning of this one to the beginning of the next one. It's not actually the length of the fragment. The fragment is delta plus this final read. And of course, if you're coming in the other direction, it's from this point to this point. So when R is 36 and delta is 200, say, then the fragment itself is actually 236 base pairs long. So the target was 200, and they came pretty close. Standard deviation was about 10. Here, the target was 400. They came pretty close, but the standard deviation jumped up to 33, and the read length to 100. And these numbers are all question marks, including the ones that I've written down. This is our best guess at what the mapping failure is. The probability that when you have a read, it just doesn't go to the right place. In this data set, with 100 base pairs, when we did the calculation at first, we thought this had gone way down, which it should. We're reading a much longer segment. It should be much easier to map it uniquely. Doesn't seem to. And therefore, I've taken away the numbers we originally had here. There's some inaccuracy in the longer reads. There's more inaccuracy. There's also a little trick that that Illumina plays in sort of, if you get a read that maps, if the middle, I think the middle 80 base pairs out of 100, if they map correctly, they will just sort of toss away the two ends. Or maybe it's only one end they toss away, because when you start the read, it should be pretty accurate. It's when you end it that it's not so accurate. So I'm not sure about these numbers, but we can, what I want to try to show you is sort of how these different problems differ, and how using the insert length, which was the thing I talked about with the mixture model, versus the hanging reads, how that depends on different parameters. So in the data set we're now looking at, for one chromosome, we estimate the parameter rho to be 0.27. We take R to be 0.1 because that seems to be a very robust value. We're looking at 6 million base pairs, but I just took 10 to the 6th. And I took the nominal value of W to be 30. So I'm not any longer trying to maximize with respect to W, except when I deal with the hanging reads for deletions. With the hanging reads for deletions, I do try to maximize with respect to W because of this thing that I pointed out right here where I'm trying to align these. Anyway, I'm not sure that's the right thing to do, but that's what I tried to do here. But what you see is that the power can be concentrated on one or the other of these. We originally thought we should be trying to combine these two sources of information. We've sort of given up on that nominally because in so many cases, and we don't know which cases they're going to be, one of these has some power and the other one has no power. And if you try to combine them, say by forming a chi-square combination, the sum of the squares of the two statistics or whatever, you just add noise to your process that has some power. There are cases where both of them have some power, and we've sort of cooked up an artificial set of cases where combining them seems to increase the power, but it doesn't help all that much compared to just taking, maybe using a Bonferroni correction to take the statistic that seems to have the most power. And the reason you can't just take the one that has the most power is it depends on what the true width of the deletion is, and you don't know that. So the insert length statistic, that is the mixture statistic, the power goes up as the insert length increases. With regard to the hanging reads, well, I'm sorry, I've messed with two parameters at the same time, but here the actual frequency of the deletion went down, but the length went up, and as far as the insert length was concerned, it really helped. When the frequency of the deletion goes down, for the hanging read, the power just gets decimated. Here's another example. Here's one where I held the frequency constant, increased the length, and you see the power of the insert length statistic goes up, but because the frequency is so low, these have no power at all. Here's an example where it's sort of the other way around. The frequency is high, the length is not close to zero. The power here would be the same even if that deletion were one base pair. And then the power here would be zero. So it's really very hard to say that one statistic is somehow better than the other or say how exactly they should be combined. Here's another example where I'm comparing insertions for the insert length statistic and the hanging read statistic. I'm comparing assertions and deletions. For the insert length statistic, it's typically easier to detect deletions. In every case here, the power is greater. I think that's not an accident. And in fact, for the insertion, notice that the power can go down even when the length goes up. And there's a reason for that too. If we have this insertion, we only get to use the insert length statistic as if we have something that maps from here all the way over to here. And that means this fragment, which we've pre-selected to be maybe 200 base pairs, has to span at least the length of the entire insertion. And so you can get insertions that are, so to speak, too long, even though that should be an easier case. You think intuitively it ought to be an easier case. If you look at the raw data, you'll see it more clearly. But if you look at the statistic, you can have the length going up and the power going down. For a while it goes up, but then it goes down. For deletions, power can only go up with length. But if you get a rare deletion, as in this case, then of course the power goes down. But if it's long enough, it doesn't hurt you too much. With regard to the hanging reads, as I said, the power for detecting a deletion is just, in this case, is not very high because the frequency of the deletion is small, but it's invariant with respect to the size of the deletion, at least in theory, assuming that when I align these up, I'm able to do it accurately when I line up these two peaks. with regard to the insertion, the power goes up with the length initially, and then it sort of levels out. And again, you can draw a picture which will show you why that is, roughly speaking, the case. So after a long time of looking at a lot of numbers, I'm beginning to generate some intuition. But this problem is very nonlinear, and you run the risk of saying something really stupid if you think that because you've looked at one set of numbers that they will apply the next time you look at a different set of numbers. For example, one of the things you might try to do, well, one thing you might try to do is, as I said, it might make sense to pool the DNA. You get more coverage, so in other words, your Poisson process will have a larger frequency or larger rate, and that's good if you combine a bunch of different genomes. But if there's only one of them that shows the insertion or deletion, then it's finding a needle in the haystack and you're out of luck. If several of them show the same insertion or deletion, then combining several genomes can actually be a cost-effective way to find that insertion or deletion. But how the numbers actually work out is something that's still a little bit mysterious to me. Okay, I had a few extra slides talking about how one can use the false discovery rate in a problem like this, but because I hope you will ask questions or make suggestions, I'm going to stop here and just give you two references, one to the part of the talk I didn't talk about, and one to a paper which is said to be in preparation in 2013. It was also said to be in preparation in 2012. And it's still in preparation. And it's one of these one step forward, two step backwards, or maybe the other way around situations where each new day, which mainly means each new look at the data, which is mainly job of Nancy Zhang and her PhD student, that it gives us more things to think about. Please do ask questions if you have any, and thank you for your attention.
You mentioned about combining different genomes towards the end of your talk. What is it a well-defined starting point of that sequence? Like in a time series, I know what time zero means, right? What is that in this kind of a data?
Well, it's whatever reference genome you're using. It's the starting point of that. Now, a real cynic would say that when you think you've detected an insertion in a target genome, it could be that there's a deletion in the standard genome, but they would look exactly the same. But the standard genome is this thing that people spent years sequencing and resequencing and so forth. So that's taken to be the noiseless truth. And that defines the parameter that I've called the running parameter T, which in principle is base pair by base pair through that genome.
Are insertion and deletions well-defined separated events, or do they get so close that the sort of noise you get in the signal anyway could actually be confounded by the fact you've got insertions and deletions going on very close to each other? Because I mean, you can almost randomly, if you have enough insertions and deletions close together, you can basically change any sequence or any other sequence.
That's true. So there could be a problem, and what appears to be the case, although this is I think more documented in the case of copy number variation, is that there are sort of weak spots, like so-called recombination hotspots, weak spots where the DNA sequence can break apart, and if it can break apart in close by one spot, close by to another spot, then you're likely to end up with an insertion or a deletion. And we're definitely assuming that we're not in the case where there are accumulation breakpoints of insertions and deletions. Although, to some extent, that might just look like one very common deletion. I'm not sure.
I don't know very much about how genetic people do this, but I have two questions. Firstly, when they're doing their reads, do they actually have the entire genetic sequence? So they presumably do map them. Do they map along the whole sequence and say A, C, T, G, and then compare that with another?
For the standard genome, yes.
Yeah. So I guess I'm wondering, but they don't do that for the reference one.
No, well, I'm sorry, that's the reference genome, but for the experimental one, the one you're experimenting with, where you hope you'll find out whether this individual that you've never seen before, where his insertions and deletions lie, then you just do these so-called paired ends, because you can't afford to do the whole genome now. That's the next generation of sequencing, where supposedly people will do the whole genome and not even think much about it. And I think they do now for some cases of some serious diseases where somebody's really focused on one disease, and he'll focus, he'll do an entire genome sequence, cost a few $1,000s, and that's that. But that's why we're talking about these paired ends, because there's these middle segments that we don't know what they are, and we're trying to infer what's going on there from the places where we do know the sequence.
So you can't go, so after you've got a suggestion that there's an insertion, you can't go back and then look at the bit in the middle and see whether it's actually.
In principle, you could. In principle, you could. And people, I should say, there's another way a lot of this is done, which is to target particular genes. So if you have a particular cancer that people think is caused by a particular gene or by some mutation in a particular gene, then you can sequence the whole gene. It's not that sequencing is that expensive, but it's not something that can be done routinely on a whole genome level for large numbers of people. And that's, in a certain sense, what we're talking about here.
And my other question, can I have another question? So again, I'm guessing that maybe doctors have a suggestion, or they have an idea as to where in this sequence the deletion or insertion might happen. And do they try and choose reads not uniformly spaced along the genome? They think, right, well, it's more likely to happen around here, so I'm going to have more reads where I think that.
Well, I think, well, there are two aspects to it, as I say. When you're talking about a specific disease, then it's likely that you are talking about targeting a particular region. But to get away from the doctors and the disease, I might say that one region for just trying to discover as many of these as you can is for use in evolutionary biology. You want to know which people are related to which other people. And so finding small polymorphisms of whatever kind. Sometimes it means finding that they have the same SNP variation at a particular location, or it might be finding that they have the same copy number or insertion or deletion at the same location. Gives you a clue as to the people that are related, and allows you to build a phylogenetic tree. And so, or coalescent tree, I guess. So there's a whole bunch of reasons you might be interested in this, and we're interested in the large scale whole genome where you don't have a target, and the fragments are selected because when you cut up the genome with an enzyme, you can sort of measure the length of what you've got, and you get rid of everything that's not of the length that you want. And that reduces, that you still have this sigma in the problem, but otherwise you've controlled for length, but not for the frequency of the fragments that you have at any particular place.
Still one more question. So can I think of the insertion as a disruption in your Poisson process? So something's going on, then all of a sudden there's a change in the process.
Yes.
And then so where the first process ends because of the insertion, and where the same process begins after the end of the
Yeah.
insertion, it's typically it's the same process. It's a
Yes, yes. Right. So, and when I was trying to sort of illustrate the difference between the paired end reads and the single end reads, that's why I said when you have a deletion here in your target genome, but there's a segment, so there's a segment there in the reference genome that's not there in the target, then you're not going to get any points that map into that region. That provides relatively little power compared to what the paired end reads combine. In fact, I could have said, maybe even should have said, that we tried to incorporate that into our statistics. So there are actually 3 sources of information, the 2 that I talked about, as well as just for deletions, just the decrease in the rate at which the Poisson process occurs. And what we found was that there's so little power that comes from that decrease. That conceptually that's the simplest, but it doesn't provide you nearly as much information as using these paired ends in conjunction with each other.
Any other questions? So if not, let's David.
Thank you.